Science Institute with a postdoc fellow from the machine learning pod, Emmanouil Vlatakis, will tell us about beyond worst case analysis of optimization in the ML era.
Okay. Yeah. Since it is a mid-fellow meeting, first of all, yes, I have a long name, but you can call me just Manolis, just to have the most important point. My name is Manolis. Nice to meet you. So this is the area that I was working during my PhD. And in order a little bit to give you an idea, another thing that you can learn about me is that yeah, and I am Greek. So my story will start with ancient Greeks. So ancient Greeks believed in regularity, that our nature is very regular. So everything that they have in their taxonomy, in their physics, was more or less based in regular shapes. That was the reason that in their physics, fire, water, earth, anything that was the basic atom of the nature was described by polyhedra with regular polygons. Now, many centuries later, a mathematician of combinatorial geometry called Norman Johnson studied this structure, and he asked a very natural mathematical question: how many different convex polyhedra you can have with regular polygons? And actually, at 1966, he described the full list of the Johnson solids, as they call it. Now, he didn't claim that this list is complete, but some years later, a Soviet mathematician, Viktor Zalgaler, proved that the list was really complete. Now, from Zalgaler's proof, it holds the following, that a solid constructed only by hexagons and pentagons cannot be a convex body, a convex polyhedron. On the other hand, some years ago, this photo has been taken, and you can go and find it in the internet. It is called the near-missed Johnson solid. And now I can ask you, you can check that it has hexagons and pentagons as construction. Now, the question is, what did we miss given the Zalgaler's impossibility theorem? And the obvious answer is the impossibilities that we have in the real world. The fact that if I ask you to accomplish that task, to create that polyhedron, you can do it. Because why? Because when you will take the scissors, you will never achieve to have exactly equal corners, equal measure in the lines. Now, what is all that connected with computer science? What is the Aesopian morale here? That the impact of the impossibility results, that we have plenty of them in computer science, and especially in theoretical computer science, the impact of the impossibility results in the real world is strongly connected about how much robust they are in the presence of noise. And if there is an important thing that I understood during my PhD is the following: if someone would like to have a mathematical theory for computer science, for example, that would explain the real world, what really you need is the following. You would like a perfect model that describes the imperfection of our world. Why? Because our world is cursed by imperfections, uncertainty, and stochasticity. And this is, if someone would like to ask me what is, I'm interested about any interesting mathematical problem, but to make it a little bit more less broad, my answer is the following. What I am really keen on working is the following. If you check out the previous century is full of results that says that any AI task that we're solving right now is somehow computational hard. However, right now we have simple algorithms that accomplish tasks that they are important in our lives. So my question in my research is the following: why do simple algorithms work so well, even in these challenging settings? If you want a very simple example, for me, the most simple example is clustering. Almost every interesting representation of clustering in TCS is NP-hard, while clustering is the easiest problem that we teach in first year ML course. So anything that I will discuss today, more or less, will be in the most important classes that we have, the class of NP, where we're asking if there is a problem, if there is a solution in our problem, and if we can check that in a polynomial time, and FNP, that it is a class where we're trying to find the actual solution. Now, the classes, the subclass of the problems that I am really interested in is the intersection of them, that it is called TFNP. Now, for all of you that you have never heard that class has the following property. Yes, if I give you a solution, you can check in polynomial time that this is a solution for an instance of a problem. And there is a mathematical guarantee that says that that problem has a solution. Now, TFNP, okay, from the theoretical computer science perspective, it is an interesting class. Why? Because it has many interesting problems, like finding a local optima in an objective function, computing Nash equilibria in games, factorization, the collision of one-hash functions. But I was wondering why really TFNP class is a trendy class, and we want to find out why the simple algorithms work on these kind of problems. From my perspective, the real answer is the following, because the humans, as algorithm designers, really like, trying to find solutions in problems that they know that a priori there exists a solution in that problem. So for the rest of the discussion, let's start with the most basic ML task. The most basic ML task that I know is the following. Let's find a minimizer of a function. And just to destroy a fallacy that people have, finding the optimal, even in a convex function, in a convex body, can be arbitrarily hard. For example, it is NP hard to find the global optimum of a convex function in the compositive programming. And if I can make it even more restricted, it can be indecidable, given that I can give you a function that the solution, the optimal solution is irrational number. So how typically we relax that? First of all, typically we ask not about exact solutions, but about epsilon approximate solutions. And the second thing that we apply as a relaxation in order to make the problem feasible is the fact that we're asking typically a local solution. Now, the first question that you can ask is, okay, we relax the problem. Did we relax it a lot? Is the relaxation meaningful? The real question that I am asking here is the following. Let's imagine that this is the objective function that we want to minimize. What we want to see is that our function is more like that. That means that a local minimum has similar performance with the global minimum of the function. And it is not like that, where the difference of a local optimum and the global optimum is really big. Okay, now, good news, let's say some good news here. From machine learning perspective, there are lots of work of Ronquet, Sijin, Michael Jordan, that proves that the majority of the machine learning tasks that we know, the objective functions, the local optimum are non-spurious. Spurious are the local optimum of that case. So now the next question that you can ask is, okay, can you explain a little bit what does it mean locality? What does it mean neighborhood? And here is a moment that I will do a separation. From the combinatorial local optimization, like the people that like SAT, for example, what is a local optimum? I will call a flip K local optimum. Let's take the max SAT that I give you clauses, and you want to optimize the gain that you have from those clauses. We call a flip K local maximum an assignment where even if you change at most K of the variables, you will never achieve to go better in your objective. This is for the combinatorial case. Now, for the continuous case, it is something that maybe you remember from the calculus. What you need actually is the local area, the local geometry is convex. This is expressed by this condition. And you want, of course, to be a stationary point. This is the first condition. Okay, now, again, from complexity perspective, these problems are more or less hard. Even trying to find the flip K1 local max for the max SAT is PLS complete. And there is a celebrated result some years ago about the continuous version of the problem, that an epsilon stationary point and generally the KKT optimal points are CLS complete. That was, I think, the best paper of Stokes some years ago. So the question now, so the real question here is, how do we tackle this problem in practice? Actually, it is just one algorithm. We start by a candidate solution, and we check around our neighborhood. And if we find a better solution, we go to that solution. And actually, this is what gradient descent is doing with, and gradient just shows the steepest choice. Now, from the complexity perspective, this algorithm is awful. PLS completeness says that there is always an exponential runtime hard instance. And there is again a result that says that for gradient descent method, what you can see is that there are instances of smooth functions that you will have exponential time. But in practice, what it happens is that, yes, combinatorial optimization works. That is the reason that we can, the airplanes can go down to the Earth, because we're solving a SAT problem during the air traffic planning. And I think that I have not to convince you that training of neural nets is working well nowadays. So what is the problem with the worst case analysis? The real problem is that worst case analysis is too myopic. We sort out an algorithm or a problem based on the brittle situation of the hard distances, while it could be the case that the general instance of the problem is easy. Now, how we can relax the worst case analysis? There are many different models. Okay, if the worst case analysis is good, then we are happy. I mean, in the worst case, we are good. So what can be in the best case? In the average case, it's a nice kind of analysis, but then I needed justification about how you randomize your input. So Spielman and Teng proposed the model of smooth complexity. For those that you have never seen that, that means that I will apply the worst case analysis, but every time that you will give me the input, I will perturb first in order to somehow sample from the neighborhood of the brittle worst case point. And I hope that in the best case, I will explain the success of an algorithm, because the smooth version of the landscape of the runtime would be like that. A similar situation holds also about where you will converge. This is a question that typically we ask in optimization. So those are some of the questions that I am interested in. With my advisor, we discussed about the binary CSPs problems like SMAXCAT, like max2SAT, Hamiltonian inizing models, and we have similar results about the case of the continuous optimization. I will stop here. I will just give you some extra questions that I'm interested in right now. What is happening when you flip not just one node, but you flip more than one nodes? And the question is if we can extend our analysis broader than just the max2SAT, if we can make it in the max KCSPs. Thank you very much.
Yeah, we have time for a quick question.
We are just on the time.
Can you say something about the higher K, the upcoming work? Just very briefly.
I mean, right now we had achieved to solve the problem for the case of two flip. Yeah, it's ridiculous to go from one flip to two flip. We're ready to discuss about that, but the real question is that one. The issue is the following. Okay, let me, in two phrases, how smooth analysis works. More or less, it is a potential argument. What you say is that at every step, every jump and every flip that you have high probability to see a lower bound of some improvement. So with a guaranteed lower bound, you know that after a polynomial time, with high probability, you will achieve to converge to a solution. Now, the issue with the max K CSPs is the following, that it is much more complicated to prove every flip influence all the other CSPs. So flips that you believed that gives an improvement very quickly can be proven in the next rounds that right now are worse. So this is the real difficulty that someone has to tackle for the general case. It is a very interesting open problem for me, and for anyone that would like to work on it, I'm happy to discuss with you. Can you repeat again? Yeah. This is about the continuous version.
Oh, the one where you introduce K-flip.
Where you have the K-flip algorithm. Oh, the K, oh, here, you mean?
Yeah. There's this work by, it's actually with the Irit and Rachel Lynn, where we.
Can you go to the microphone? I can.
There is a work on correlated instances where you have like a CSP instance.
Okay.
And you have a whole bunch of CSP instances actually that are given to you. And you know that the answer for all of them have answers.
Okay.
And you know that the answers are correlated to each other via this kind of
Okay.
flipping.
Interesting.
So if you take the answer to one, you do some flips, in a sense, that's not exactly, but I think it translates that you do some flips, then also each one of them can be answered by some flipped version. And if you're given all these instances without the solutions, but you know that the solution has this correlation, then you can solve in polynomial time.
Oh,
so maybe it's interesting to look at.
Yeah. First of all, thank you very much. I wasn't aware about the result.
No, I don't know how, but it feels like it might be related. Yeah.
Yeah.
It's because it's all about taking statistics about the answer for each location.
Oh, so you say maybe there is like what smooth analysis gives you that you collect somehow the neighborhood.
But you have an extra assumption, and that is somebody gave you a bunch of correlated instances.
I see.
And I wonder if that if you can imagine analyzing that situation as an input rather than a single
the correlation.
So the correlation model, you could come up with your own models, but this particular model is that if you take the solution and you flip each solution by a certain amount, but even a small amount or large amount.
So
like 1 minus epsilon.
What I am thinking from your sentence is the following, that the correlation that you describe is combinatorial.
Right.
The correlation that it is described by the
smooth analysis
is statistical.
Right.
That I'm just collecting different instances, but somehow it is very interesting. I want to check the paper. The one sentence that probably I can say is the first thing that I would like to see is when I collect instances around. That it is like the input. I'm taking the input here.
No, because if I could collect instances, then I have a polynomial time algorithm. But I don't. The point is that it's given. So if I somehow, at least in the places where it's interesting, you can't collect it because it gives you a much faster algorithm than we usually know.
I see.
So what you get the strength from is that somebody somehow is given. Like, why is it a reasonable assumption somebody's given? You know, the intuition is that we say that there no instances that we care about really isolate. Exist in nature. That we often there's a lot of instances which are kind of related to each other, and conjecture here is that they're related through the solution space. That we never really invent any, the problems out there, they're all kind of perturbations of each other. So why not take advantage of the fact that we have all those problems, and the solutions are related, and maybe this way we can find this. We can define a bigger problem, maybe where the solution is unique or something that might be a technique.
Okay, I promise that I will check the paper, and I hope Next year, I will be 2 years here. Next year, I hope that I will have an answer.
Yeah, we'll take you up on that. So, okay, thanks to all the speakers of the session. We have a short break now and we'll reconvene at 11:30. Thank you.